This slide deals with convective mass transfer. This is Newton's law. You can obtain the heat transfer coefficient, H, in watts per square meter per Kelvin, from the Nusselt number determined as indicated in Table 8.4, for flow in a circular tube. The table is given below, with only the correlation for turbulent flow included, as an example. The correlation is used for heat transfer from a surface to a moving fluid. You will also come across mass transfer from a surface to a moving fluid. In the animation, you will see that the transfer of molecules to a moving fluid is analogous to the transfer of heat to a moving fluid. In the animation, you can see that the mass transfer rate is a combination of diffusion and of advection, similar to what you saw early on in the course, for convective heat transfer. For convective mass transfer, you can write a similar equation for mass transfer rate, in moles per second, or n dot. Here the driving force is the concentration difference, rather than the temperature difference, as in Newton's law of cooling. At the bottom of the table, in the fine print, you can see that all the heat transfer correlations can also be used for mass transfer. The Sherwood number, that replaces the Nusselt number, contains the mass transfer coefficient, H, m, which is in the mass transfer equation. Instead of the thermal conductivity, in the Nusselt number, you have the diffusivity, in the Sherwood number. For the Schmidt number, V, is the kinematic viscosity, which is viscosity, divided by density. This is the correlation for mass transfer, from a pipe surface made of naphthalene, to the gas moving turbulently in the pipe. You need to specify all the physical properties of the gas, as this is where the mass transfer is taking place. Is N, in the equation, equal to 0.3, or 0.4? This is a difficult question, because, for mass transfer, T, S, is equal to T, M. Maybe you can use 0.35. This slide deals with the two-film theory. You have two fluid phases, for example air and water. A gas diffuses through the phase 1 film, crosses the interface, and then diffuses further through the phase 2 film. The mass transfer equation, using a mass transfer coefficient, can be written for the gas in phase 1. The equation can also be written for the liquid in phase 2. Usually, the concentrations in the phases, at the interface, are assumed to be in equilibrium. You can use Henry's law, which holds for low concentrations, to reflect this.